All right, today we're going deep on small modular reactors, or SMRs. Not a surface-level nuclear is good, nuclear is scary take. We're going to unpack the actual tech stack, coolants, neutron spectrum, outlet temperature, fuel, passive safety, and the commercial reality. Because the global energy system is being reorganized, like structurally. We're trying to cut emissions, decarbonize heavy industry, and meet a rising demand for reliable high-density power all at once. And inside this chaos, SMRs are being pitched as a kind of firm power backbone that can support grids filled with variable wind and solar. So if you care about AI data centers, industrial process heat, replacing coal plants, or just keeping the grid stable, you're going to hear SMRs come up again and again. Let's define the thing properly. The report uses the IAEA framing. SMRs are advanced reactors up to about 300 megawatts electric per unit. That doesn't mean small equals simple. The core claim is modularity changes the economics and project risk profile. Traditional large nuclear, those gigawatt-scale megaprojects, have a long track record of scheduled delays and cost overruns. The SMR pitch is move a big chunk of construction from the field into factory fabrication, standardize the design, and build many of the same thing. This is the core bet. We trade the old economies of scale mindset for economies of series, standardized, repeatable production. Here's the fun part. SMRs are not some brand new invention. The conceptual origins are basically naval propulsion. The report points to USS Nautilus, 19 alpha power, a compact pressurized water reactor, proving that a nuclear steam supply system could be integrated in a space-constrained platform. But the industry then went the other way. It scaled up hard in the 70s and 80s to chase economies of scale, reaching unit sizes above 500 LP. The SMR comeback happens when huge nuclear projects became financially inaccessible. Capital requirements got extreme. Then in 2010, DOE pushes the plug-and-play modular solution. Build in factories, ship to sites, reduce on-site complexity. Now we go technical. The report classifies SMRs largely by coolant, neutron spectrum, and operating temperature, and that combo determines efficiency, safety behavior, and what you can use the heat for. I want you to think of SMRs as a platform category, not one reactor. 1. Evolutionary light water SMRs, LWR SMRs. These are the nearest term commercial segment, about 32% of designs under development in the report. They use regular water as coolant and moderator, so the regulatory pathway is more predictable because we know the materials and operating experience. Key design move, integral architecture. Steam generator and pressurizer inside a single pressure vessel. That reduces external piping, which reduces the risk profile for certain loss of coolant scenarios. 2. High-temperature gas-cooled reactors, HTGRs. These use helium coolant and graphite moderator. The headline, higher temperatures, roughly 700 degrees to 950 degrees. High temperature isn't just a flex. It's what makes HTGRs ideal for industrial process heat, steam, and even high-temperature electrolysis for hydrogen. And HTGRs are where you often see TRISO fuel, uranium kernels wrapped in multiple carbon and silicon carbide layers, micro-containment for fission products, stable even beyond 600 degrees in the report. Technically, TRISO is containment at the particle level. Instead of relying solely on the plant to retain fission products, the fuel itself is engineered to keep them trapped under extreme conditions. This is one reason HTGR designs talk about inherent safety and potentially smaller emergency planning footprints later. 3. Liquid metal fast reactors, fast neutron reactors. These use coolants like sodium or lead. Fast spectrum reactors can run longer cycles and can enable closed fuel cycle strategies. The report notes the attraction, good heat transfer, and operation near atmospheric pressure, which changes mechanical stress and design constraints. Fast spectrum matters because it changes neutron economy. You can design for longer refueling intervals and potentially use fuel more efficiently. Also, where waste transmutation arguments often show up later in this video. 4. Molten salt reactors, MSRs. Here, the coolant is molten fluoride or chloride salt, and in many designs, the fuel is dissolved in the salt. The report highlights a key physics safety idea. Temperature increases cause salt expansion, naturally slowing the reaction rate. The big engineering pivot is low pressure plus high temperature operation, which sounds amazing. But materials, corrosion, and licensing maturity are non-trivial. 5. Microreactors are a subcategory, up to about 30 MW and designed for extreme portability. Some concepts fit a standard 20-foot shipping container. These target remote communities, mining sites, and military environments, replacing diesel generators. Now let's talk market pull. The report is very clear. SMRs are being pushed by 3 converging needs. First, AI and data centers. Reliable, 24/7 carbon-free power. AI and hyperscale computing require near-constant uptime. Think 5 nines reliability. Intermittent renewables can supply a lot of energy, but matching reliability requires massive storage and grid capacity. The report frames SMRs as a dispatchable solution that can be co-located with data campuses, bypassing grid congestion. It also notes big tech companies securing SMR capacity via PPAs and partnerships. This is presented as a shift where private sector becomes a major off-taker and financier. So instead of government builds nuclear, it starts to look like data center needs power. Go shopping for firm, clean megawatts. Second, industrial decarbonization and process heat. Heavy industry needs heat, often high-temperature steam. That's a huge emission slice because it's mostly fossil today. The report highlights HTGR suitability for industrial steam and high-temperature applications. Third, grid stability in a high renewables world. SMRs are pitched as firming capacity, providing stability services and supporting grids with high variable renewable energy penetration. SMR value props, firm power, heat, and modular deployment. Here's where many SMR conversations get real. The central economic thesis is economies of series can beat economies of scale, but only after you build enough units. Let's look at CAPEX and financing risk. SMRs reduce the absolute capital outlay. Instead of 10 by 30 by mega projects, the report frames modules as roughly 1B 3 by per $300 Mendatabawi module, comparable to other large infrastructure projects. Lower absolute CAPEX changes financing. More entities can fund it. Risk is bite-sized. Next is construction time and interest during construction. The report says The goal is moving up to 80% of work from site to controlled factory environments. That aims to shorten on-site construction from 8 to 12 years to 3 to 5 years for modular units, reducing IDC costs. IDC is brutal. The longer you build, the more capital sits there not earning revenue. Cutting years off the schedule can matter as much as the reactor design itself. Then there is the Folk Cliff, new-scale UAMPS as the warning sign. The report points to the Folk Challenge. Early projects can get expensive. Example, NuScale's UAMPS project. Estimated LCOE nearing $90-$100, and then the project was canceled in late 2023. So yes, folk can be painful, but knock. The whole model depends on repetition. The report says competitiveness comes with no-OC deployments, standardized components, established supply chains, driving toward $4,500 targets in the U.S. to Europe by 2040. Folk hurts, but NOC wins if serial production happens. One of the most strategic SMR use cases in the report is repowering retiring coal plants. This is important because coal sites already have what nuclear projects struggle to get: transmission interconnections, switch yards, cooling infrastructure, roads, and industrial zoning reality. The report cites DOE analyses 2022 and 2024. About 80% of current and recently retired coal plant sites in the U.S., over 300 locations, are suitable for advanced nuclear hosting. And the benefits are super concrete. Infrastructure reuse can save up to 35% of construction costs by repurposing transmission connections, cooling towers, and civil assets. Jobs and wages. Nuclear sites can support about plus 650 permanent jobs and wages 50% higher than regional average, positioned as a just transition story. Environmental improvement. Replacing a single coal plant with an SMR can reduce regional emissions by up to 86%, while eliminating particulates linked to respiratory and cardiovascular disease. This is why policymakers like the COQ narrative. You're not just decarbonizing, you're repurposing legacy infrastructure and preserving economic activity in coal communities. Now we hit the bottleneck that can quietly kill timelines: fuel. Many advanced SMR designs require HALEU, high-assay, low-enriched uranium, enrichment between 5% and 20% U-235, compared to conventional reactors at 3 or 5%. That higher enrichment supports longer cycles and more compact core designs. But the report highlights a serious issue. Prior to 2024, Russia held a global monopoly on commercial HALEU production, creating a geopolitical hurdle for Western deployment. In response, the U.S. and Europe launched multi-billion initiatives to build enrichment capacity. Centrus began demonstration-scale HALEU production in Ohio in late 2023, and others are expanding capacity to meet projected demand of 10 tons year by 2030. So the best reactor design on PowerPoint is still limited by whether you can actually source its fuel at scale, reliably, politically. All right, last segment: safety, waste, and the license to operate. The report emphasizes passive and inherent safety features that rely on physics, not active systems. In conventional reactors, cooling depends on pumps. SMR designs can maintain cooling via natural convection and gravity-fed water tanks. designed to be walk-away safe for days or even longer without external power. And TRISO fuel is highlighted again as meltdown-proof fuel in the report's framing. Uranium kernel plus carbon silicon carbide layers retaining fission products at extreme temperatures, supporting the argument for potentially reduced emergency planning zones. The report includes a serious debate. A 2022 Stanford plus University of British Columbia study argued SMRs could produce higher volumes of low-intermediate waste per unit energy due to greater neutron leakage activating structural materials. For specific designs studied, spent fuel volume could be up to 5x higher, and radiotoxicity just 50% higher after 10,000 years compared to conventional plants. Then the rebuttal. Industry and experts argue those findings used outdated or non-optimized designs, and that advanced fast-spectrum or liquid fuel reactors could reduce long-term radiotoxicity via transmutation, plus strategies like deep burn cycles or recycling. So the honest takeaway is, waste isn't a settled PR bullet point. It's a design-dependent, fuel cycle-dependent argument, exactly the kind of thing that matters in deployment debates. The report says the old regulatory model, designed for bespoke mega projects, is ill-suited for modular factory units. It points to the IAEA's Nuclear Harmonization and Standardization Initiative, NHSI, launched in 2022, aiming for multinational joint reviews and a type certification direction similar to aerospace. Let's close with a practical set of takeaways. SMRs are not one technology. They're a family defined by coolant, neutron spectrum, temperature, and fuel strategy. The economics hinge on serial production. Falk is painful. New-scale UAMPS is the cautionary tale. NOAK is the business model. Coal to nuclear repowering could be the fastest strategic path because sites already have grid infrastructure and community workforce pathways. HALEU supply is a gating factor for many advanced designs, and it's now a geopolitical and industrial capacity issue, not just engineering. Safety improvements are real in design philosophy. Passive cooling and TRISO are central narratives. But waste and fuel cycle debates remain live and design dependent.